Welcome to my channel, Learn with Shobha Mehta. Today we will discuss about semiconductors, intrinsic and extrinsic, and energy bands. Semiconductors are materials whose conductivity lies between the conductivity of good conductors and insulators. Now, semiconductors examples, germanium and silicon, they are 14th group elements. They have 4 electrons in the outermost orbit, tetravalent atoms, and these 4 electrons in the outermost orbit, they form covalent bonds with the neighboring germanium or silicon atoms. Now, at the normal temperature, there aren't many electrons which are free, so conductivity of a pure germanium or silicon semiconductor is very low. These semiconductors whose conductivity is only due to germanium and silicon atoms, no impurity, are known as intrinsic semiconductors. So their conductivity is low because the electrons and holes are thermally generated only. That means electrons gain energy depending upon the temperature of the material, semiconductor, silicon, germanium, and if it is enough, it overcomes the bond energy and then moves out and becomes free. So electrons conduct in conduction band, holes conduct in valence band, but the conductivity is not much. They're not much useful in the electronic appliances, devices. Therefore, impurities have to be added. Now, these semiconductors in which we have suitable impurity atoms are extrinsic semiconductors. Now, what we add is we add the atoms from the 13th group of periodic table and 15th group of periodic table. 13th group will be aluminium, indium, gallium. They have 3 electrons in the outermost orbit. So when they occupy the lattice positions, 3 electrons form the 3 covalent bonds with the neighboring germanium atoms, whereas the 4th bond, there is a vacant site. This vacant site is known as a hole. It is equivalent to a positive charge because it is absence of electrons, absence of negative charge. Now, this is known as a hole, a vacant site, and how this p-type will conduct. An electron from a neighboring covalent bond will jump into this vacant site in another bond, and so the hole shifts. Now, the hole shifts in valence band, whereas an electron, free electron, moves in the conduction band. So in an extrinsic semiconductor, conductivity increases manifold because of these impurity atoms added. Now, this is the p-type semiconductor. In n-type semiconductors, pentavalent atoms from the 15th group are added. These have 5 electrons in the outermost orbit. 4 electrons form normal bonds, covalent bonds with the neighboring germanium atoms, whereas the 5th electron is very loosely attached to the parent impurity atom, which is the donor atom, because it is donating electrons. So N type of semiconductors have impurities like antimony, bismuth, etc. These impurity atoms, they donate 1 electron per atom, so the conductivity increases. Now, how much impurity is added? It's 1 ppm, 1 part of impurity atom per million part of host atom. This is the amount of impurity added, and this is enormous. So lots of electrons in the case of n-type and lots of holes are created in the case of p-types, and conductivity increases. So p-type and n-types are used extensively in various devices like p-n junctions, n-p-n transistors, etc. In the n-type semiconductors, majority charge carriers are electrons, minority charge carriers are holes. In p-type semiconductor, majority charge carriers are holes and minority charge carriers are electrons. But remember, the total charge on a p-type or an n-type is 0 because on the whole it is neutron. Number of electrons is equal to number of protons. In solids, semiconductors, we talk of energy ranges. Electrons can occupy certain energy ranges rather than energy levels as in individual atoms. Now, in the case of semiconductors and solids, valence band is the energy range which the electrons can occupy, but they are not helping in conduction. Higher to this is energy range forbidden energy range, forbidden band, which the electrons cannot occupy. Above this is the energy range, conduction band, energy range which the electrons can occupy. They gain energy, move on to conduction band. This means they are helping in conduction. Now, on the basis of the forbidden energy range, we divide materials into good conductors, bad conductors, and insulators. Now, like carbon, silicon, germanium, all are 14th group tetravalent atoms. But carbon is an insulator, bad conductor, because its energy range is very high, 6 electron volts, whereas the energy level of silicon is 1.1 electron volt. Forbidden band energy range in germanium is 0.7 electron volt. So, in these two cases, semiconductors, electrons are gaining energy. They can easily move on to conduction band, become free and help in conduction. Now, in the case of p-type semiconductor, due to the acceptor atoms, a new energy level is created near the valence band. In the case of n-type semiconductors, due to the donor atoms, a new energy level is created near the conduction band. So remember these diagrams very well, and you will surely master this chapter.